The order is the period of a certain function, and therefore we could now think about applying the period finding algorithm to this. However, for this we would also need the corresponding function gate. It turns out that it is much simpler to instead define a certain unitary operator u that implements this function in a much more direct way. This operator u acts on the computational basis states x and simply replaces them by this expression here. So one computational basis state is just replaced by another one. Well, to keep this reversible, we have to constrain x to this range here. And therefore we define that this unitary operator is not doing anything to the states outside of that range. So this is just a permutation of the computational basis states, essentially a classical operation. And this means that we can also very efficiently implement these powers of this operator. So this looks very useful for phase estimation, and therefore we should now look what we can learn from the eigenvalues. And it turns out that these eigenvalues indeed depend on the order R. Let us start with the corresponding eigenstates, and these can be written in the following form. We give them an index n, and then we have a sum here, which runs from 0 to r minus 1, and then we have some exponential factors of this form here. And then we have a certain sum of computational basis states given by these expressions here. And we can then check that this is indeed an eigenstate by applying the operator u. So this gives us an additional multiplication by a in here, and in other words we obtain here the power z plus 1. And now we can relate this to our original state by shifting the summation index z. We are allowed to do so because these factors here wrap around the unit circle, so this is indeed periodic with period r also in this variable z. And when we then shift z by 1, we obtain one extra factor which we can pull to the front, and this is this factor here. And all the rest is just our state un. And so this is then our eigenvalue, and we see that it indeed depends on the period r. And it indeed enters this eigenvalue as a complex phase factor in the very same way as it did in the period finding algorithm. But here we want to apply phase estimation, and for this we just need one more thing, namely a suitable state to feed into the unitary operator u. For this we cannot use these eigenstates because they themselves depend on this unknown period r. Therefore we are going to use a strategy that we have already employed before, namely we are going to use an initial state that is fixed but has a known relation to all these eigenstates. And this turns out to be the straightforward superposition of all of these eigenstates. So when we add them all up with equal weights, then we obtain the computational basis state 1. So this is a state in which all the quantum bits are in the state 0, with the exception of the last one, which is in the state 1. And this again comes from these complex factors here. When we sum over n, then we obtain something finite only when z is equal to 0. But before we applied u, we had just z at this place, and when we set this one equal to 0, then we get a to the 0, which is just 1, but modulo m, this is still also 1. And therefore this gives us constructive interference for this computational basis state, and we obtain this state here. And with this we have everything that we need when we apply phase estimation to this initial state. And then carry out the measurement, we obtain a certain integer, and this we can then interpret as an n-bit approximation of this rational number here. And then we can apply continued fractions to obtain some information and candidates for this period here. So this is the way that we can determine this order on a quantum computer, and it is very efficient even when we deal with very large numbers. In particular when we compare this to what we can do on a classical computer. And when we then combine this with our considerations on prime factorization, this becomes the Shor algorithm. So all that remains to be done is to summarize how this algorithm works. We start out with an integer m, which is known to be the product of two prime factors, but we do not know which factors these are. And this is a relevant scenario because this is used in asymmetric key cryptography. Next we pick a number a, and initially this is just an arbitrary number, but we will later see whether this was a good choice. And we work out the order of a mod m. And the first thing that we do is to check whether r is even. If it isn't, then we are going to start again with a new number a. And we will do this as many times as we need to end up with an even r. And so then we will have an even r, which we can then write as 2 times another integer. And therefore we can form our two candidate numbers, namely this number here and this number here. Here we will check that neither of these numbers is just a multiple of m itself. If that's the case, then we also have to start again. And then we apply the Euclidean algorithm to these numbers to find the greatest common divisor of these numbers with m. And this rapidly converges and gives us the prime factors p and q. Consider, for instance, a case that we carry out the Shor algorithm for m equal to 21, where we have selected a equal to 11, and we implement this in a system with 10 quantum bits. 9 actually would be enough in that case, but that's just for illustration. So curly n would be 1024. And then we carry out the phase estimation in the order finding process with that unitary operator and make a measurement of x. The probability of x would then come out to be like this. This would return a number, x between 0 and 1023. And there would be 6 peaks. One that's essentially the same one around 0, and then a further 5 in between. They are all equally spaced. And so that would be looking roundabout like this. And one of them is, for instance, close to x equal to 171. And then just for illustration, if your measurement, for instance, returned the value x equal to 172, which is close to this, just to illustrate that it doesn't need to come out exactly like this, then this would tell us that n over r has to be close to 172 divided by 1024. And that's actually the same as 43 divided by 256. So there are just some multiples of 4 that we can cancel immediately. Then we can apply continued fractions to obtain some other rational numbers close to this. And we indeed carried this out exactly for this example and obtained these two candidates here. And in particular, this one here gives us a candidate for r which is even. So we can then try to make some progress with this number. So r would be 6 and r prime would be 3. And our two candidate numbers sharing some possible factors with m would be these two numbers here. And so these are again the numbers that we worked out before. First we check that these numbers are not indeed divisible by m themselves, but we find that they aren't. And then we conclude that they must contain some of the factors distributed over these two numbers. And these will then be the greatest common divisors of these numbers with m. And so we can figure them out by applying the Euclidean algorithm. And as described before, this will give us the values 7 and 3. And then we can see that these are indeed the prime factors of 21. So this is how the Shor algorithm works for this particular example for m equal to 21. So in summary, this algorithm really puts everything together into one coherent and efficient scheme. The Shor algorithm has indeed been implemented in physical systems already in the early 2000s but only for very small numbers of qubits. And so the very first number that has been factorized in this way was 15, and the numbers haven't become much larger since. And the reason for this is that quantum computers are very difficult to build. But how this comes about is very interesting in itself, and therefore we now move away from these applications to a new question, namely how to make quantum computers more resilient and reliable.